Okay, welcome back. So in this video, we're going to go over chapter 2, Lieberman, and chapter 2 is entitled Basic Plasma Equations and Equilibrium. And in this, we're going to get introduced to a lot of core equations, as well as some ideas on how to simplify them that the rest of the text is going to respond to, is going to kind of reference back to pretty regularly. So let's go ahead and get started. Okay, so Chapter 2, Basic Plasma Equations and Equilibrium. 2.1, Introduction. The plasma medium is complicated, that's true, in that the charged particles are both affected by external electric and magnetic fields and contribute to them. The resulting self-consistent system is nonlinear and very difficult to analyze. Furthermore, the interparticle collisions, although also electromagnetic in character, occur on space and timescales that are usually much shorter than those of the applied fields or the fields due to the average motion of the particles. So, um, the plasma itself. So if I draw this, let's just draw a box. If this is my, chamber, I have some plasma on the inside. The plasma itself, of course, is made up of electrons. So we have some electron density, some ion density. And these electrons and ions are themselves emitting an electric field. So on account of the plasma itself is, made of these ions and electrons, it creates its own field. But of course, if we apply an electric field macroscopically uh, over our entire chamber, those electrons and ions are going to respond to that field. So they themselves are responding to a field, and they themselves are also generating their own field. Furthermore, they're colliding with each other. Yeah, all that is to say, it makes a difficult problem. And while this chapter will introduce kind of the formal equations to describe it, our goal is to take those formal equations and then simplify them down into something that's tractable. Okay, continuing on. To make progress with such a complicated system, various simplifying approximations are needed. The interparticle collisions are considered independently of the larger scale fields to determine an equilibrium distribution of the charged particle velocities. The velocity distribution is averaged over velocities to obtain the macroscopic motion. The macroscopic motion takes place in external applied fields and in the macroscopic fields generated by the average particle motion. These self-consistent fields are nonlinear, but may be linearized in some situations, particularly when dealing with waves in the plasma. The effect of spatial variation of the distribution function leads to pressure forces in the macroscopic equations. The collisions manifest themselves in particle generation and loss processes as an average friction force between different particle species and in energy exchanges among the species. In this chapter, we consider the basic equations that govern the plasma medium, concentrating attention on the macroscopic system. The complete derivation of these equations from fundamental principles is beyond the scope of the text. We shall make the equations plausible and in the easier instances supply some derivations in appendices. For the reader interested in more rigorous treatment, references to the literature will be given. Like he says here, the detailed derivation is complicated and beyond this text, but some kind of simplified explanations will be given. On this point of the collisions are going to be treated separately, and that's going to be the collisions between the particles are treated separately than the motion of the kind of macroscopic system, and that's going to be the subject of chapter 3. We'll be dealing with these interparticle collisions. And this process is going to be very similar to uh, the solution to the Navier-Stokes solution to fluid equations. So, we'll see that as we go on. In section 2.2, we introduce the macroscopic field equations and the current and voltage. In sections 2.3, we introduce the fundamental equation of plasma physics for the evolution of the particle distribution function in a form most applicable for weakly ionized plasmas. We then define the macroscopic quantities and indicate how the macroscopic equations are obtained by taking moments of the fundamental equation. References given in the text can be consulted for more details of the averaging procedure. Although the macroscopic equations depend on the equilibrium distribution, their form is independent of the equilibrium. To solve the equations for a particular problem, the equilibrium must be known. In section 2.4, we introduce the equilibrium distribution and obtain some consequences arising from it and from the field equations. The form of the equilibrium distribution will be shown to be a consequence of the interparticle collisions in Appendix B. Okay, so let's get started with our fundamental forces. So section 2.2, field equation, current, and voltage. Maxwell's equations. The usual macroscopic form of Maxwell equations are the curl of the electric field is equal to the time rate of change of the magnetic field. The curl of the magnetic field is the sum of the change of the electric field plus any currents. The divergence of the electric field is equal to the charge density. And here the divergence of the magnetic field is 0 on account that there's no magnetic monopoles. So um, uh, each of these are vector quantities. So they have, a spatial and temporal dependence. So, for example, when we see this row here, this row will really have some spatial and temperature, excuse me, spatial and time dependence, as well will the electric field and the magnetic field, and the current here. So going on, where E of RT and H of RT are the electric and magnetic field vectors, and where mu naught is 4 pi times 10 to the minus 7th, um, and epsilon naught is 8.84 times e to the 12 minus 12. They are respectively the permeability and permittivity of free space. The sources of the fields, the charge density, rho, and the current density J are related by the charge continuity equation. So um, this equation here, time rate of change plus the divergence of J is equal to 0. And uh, in general, the current is the sum of these three different currents, so a conductivity, a polarization, and a magnetization, with both the polarization and magnetization only occurring inside of a uh, polarizable material. And these will usually be, and he talks about this in the next section, these will usually just be considered to be small. And this equation here, the time rate of change of the density plus the divergence is equal to 0. Can kind of just be, if we imagine in 2 dimensions, the divergence is, outward movement. So if we have charged particles that are moving out of some boundary, uh, uh, you know, the particles are not created or destroyed. So if there is some loss in time, it's because there is this movement out of the boundary of the particles. Okay, continuing forward, where the conduction current density is due to the motion of the free charges, and that's what we're going to be mainly concerned about. The polarization current density is due to the motion of bound charges in a dielectric medium, and the magnetization current density is due to the magnetic moments in a magnetic material. In a plasma, in vacuum, polarization and J polarization, J magnetization are 0, and J is just equal to the conduction. So if we in this case, the currents that are generated inside the plasma will be due to, these kind of macroscopic flows of charge. So if 2.2.3 is integrated over a volume enclosed by some surface S, then we obtain the integral form of Gauss's law. Okay, where Q is the total charge inside of the volume. Similarly, integrating 2.2.5, we obtain yes, the time rate of change is simply the integral over the surface of the dot product of the current with the differential area element. And again, what this is saying is if current is the flow of charge, if we have some bounded surface here, in order for you to lose charge out of the boundary S, the current has to flow out. So J is the flow, area, dA is the differential area. So if this is some sphere, we have to integrate over the entire area of the sphere, and any charge loss out of that bounded surface, like I said, is due to the current flow. Okay. In 2.2.2, the first term on the right-hand side is the displacement current density flowing in the vacuum. So going back to 2.2.2, so we have our third, our second of Maxwell's equations here. So we have the curl of the magnetic field has two source terms, either a flowing current or the displacement current, so the time rate of change of the electric field. Okay, in 2.2.2, the first term on the right-hand side is the displacement current density flowing in the vacuum, and the second term is the conduction current density due to free charges. We can introduce the total current density, J sub t, as the sum of these, and taking the divergence of 2.2.2, we see that the divergence of the total current is equal to 0. So again, if that's true, if we can basically replace this equation here with J, just total current. And if there is under a situation where there's, it's in steady state, that total current will be the total divergence will be 0. In one dimension, this reduces to the differential of J with respect to X is equal to 0, such that JT is independent of X. Hence, for example, the total current flowing across a spatially uniform one-dimensional discharge is independent of X, as illustrated in figure 2.1. A generalization of this result is Kirchhoff's current law, which states that the sum of the current entering a node where many current carrying conductors meet is 0. This is also shown in figure 2.1, where current RF is equal to the total current plus current 1. So if we look at that figure real quickly, this is kind of our first introduction to an equivalent circuit model for the plasma. And we'll come back to, over the course of the text, Lieberman developed several of these equivalent circuit models where, usually you'll see Kirchhoff's law in sort of an electronics textbook. But the idea is that we can have these kind of different um, parts of the plasma where current has to flow, and we just have to conserve current. So if there's going to be current, this total current RF gets split between some capacitive branch and then the plasma itself. The current can't be created or destroyed, it just gets split between the two. And what we'll develop next, again, is the Kirchhoff's voltage law, which says that after we loop through this entire circuit, the total voltage is 0. So if voltage is driven up at some point, it has to drop at some other point. So right here, so if the time variation of the magnetic field is negligible, as it is often the case in plasmas, then from Maxwell's equation, the curl of E is approximately 0. So if we go back and we just say that there's not this dramatic generation of the magnetic field, it's either static or slowly varying, we approximate this as 0, making del cross E just equal to 0. And that's going to mean that, and this you'll find this in a calculus textbook or an electromagnetics textbook, but if the curl is 0, then it means that the electric field is simply the gradient of a potential function. So the potential is a scalar function, which then gets turned into a vector function by applying the gradient here. I think I said curl. So if the curl is 0, then we can just take the gradient of the scalar potential field. So since the curl of a gradient is 0, this implies that the electric field can be derived from the gradient of a scalar potential. Integrating 2.2.9 around any closed loop C gives us this expression here, and which is just a formal, I guess is a mathematical way of writing Kirchhoff's voltage law, which states that the sum of the voltage across any loop is 0, which is illustrated in 2.1, for which we obtained voltage RF right here. Voltage RF is equal to voltage 1 plus voltage 2 plus voltage 3. So any closed loop, we can either do this loop here or we can do this loop here. Any closed loop will have a sum of 0. So in this case, voltage RF is the applied, sinusoidal voltage. And then across the plasma, there's these 3 characteristic zones. Again, there's the voltage on each sheath, and then there's some voltage across the plasma here. And Kirchhoff's voltage law allows us to relate the two. In 2.2.9, it is substituted into 2.2.3. We obtain that a grad squared phi is equal to minus rho epsilon. So if we just go back, all we're doing is we have the third equation here, and I'm just going to do grad dot E. I'm going to move epsilon to the other side. But because the curl is 0, we can say that E is equal to minus grad phi. So plugging this in for there, we get grad phi is equal to rho over epsilon naught, minus rho over epsilon naught, which, again, we just say epsilon naught there. Okay, yes, and we recover our equation here. So equation 2.2.11, Poisson's equation, is one of the fundamental equations that we shall use. As an example of its application, consider the potential at the center, x equals 0, of 2 grounded, phi equals 0 plates, separated by a distance L equals 10 centimeters, and containing a uniform ion density, without the presence of a neutralizing electrons. Integrating Poisson's equation here using the boundary conditions, phi equals 0 and x equals plus or minus L over 2, and that d phi dx equals 0 and x equals 0 by symmetry, we obtain a potential profile that's a parabola. Now, the maximum potential at the center, which is impossibly large for a real discharge. Hence, the ions must be mostly neutralized by electrons, leading to a quasi-neutral plasma. So this is just a solution for the plasma if there was no electrons, which of course in the plasma there are electrons, but he's just showing that there's simple solutions to this equation. It's a second order ordinary differential equation. So figure 2.2 shows a particle in cell simulation, time history over 10 to the minus 10 seconds of A, the velocity space, B, the number of sheets versus time, and C, the potential phi versus x for 100 unneutralized ion sheets with E over m for argon ions. We see that ion acceleration in A, the loss of ions in B, and the parabolic potential profile in C, the maximum potential decreases as ions are lost from the system. We consider quasi-neutrality further in section 2.4. So, so this is just a simulation. Again, particle and cell is, and I really want to go into depth in a future video on particle and cell. But in a 1D case, the simulation is populated in with these sheets of ions, no electrons, and then at each time step, numerically, the potential is solved for based on the local ion densities. And then those ion densities are used to basically update to push around those sheets of charge. So at time t equals 0, there's this kind of nice parabolic profile. But over time, because they are accelerated out of the simulation, the overall charge is dropping. So eventually you would drop to just 0 charge if there's no generation term. Okay. Moving forward, electric and magnetic fields exert forces on charged particles given by the Lorentz force law. So this is going to be a kind of our main force that's going to be affecting the charges in our system. So we have a force due to the electric field, and then we have a force due to the magnetic field as well as the velocity of the particles. Okay, here V is the particle velocity and B is equal to mu naught H. Which is labeled here the magnetic induction vector. The charged particles move under the force of the Lorentz force. The charged particles move under the action of the Lorentz force. The moving charges in turn contribute to both rho and J in the plasma. So again, this is kind of the self-consistent problem that the charges themselves are being pushed around by electric forces, and then the charges themselves are also the source of these forces. So you need to solve it both to get a full solution. So if rho and J are linearly related to E and B, then the field equations are linear. As we shall see, this is not generally the case for a plasma. Nevertheless, linearization may be possible in some cases for which the plasma may be considered to have an effective dielectric constant. That is, the free charges play the same as a bound charge in a dielectric. We consider this further in Chapter 4. Chapter 4 is where we're going to introduce a lot of kind of plasma waves. All right, so now we're going to move on to section 2.3, the conservation equations. And in my opinion, these equation, Boltzmann's equation, in this sort of section is really kind of the most fundamental. So in section 2.2, we're introduced to some conservation equations as well as Maxwell's equations. And that's really going to be how we describe the fields that are generated. But the more kind of fundamental, in my opinion, kind of the more fundamental thing is this following section. So for a given species, we introduce a distribution function, f of r, v, and t in the 6-dimensional phase space, rv, of a particle position and velocities with the interpretation that this function here is the number of particles inside a 6-dimensional phase space volume, d cubed r dv v at rv at time t. So this is the, if we consider just one dimension or 2 dimensions, so x in the bottom and velocity in x in the top, there's going to be the particles will populate inside here. And that's what this next photo, but the central idea is that there's some function that actually describes the way that the particles are dispersed inside a phase space. And what we'll see is that in certain scenarios, this is a kind of simple, it's not that simple, but it's at least a analytical equation described in the Maxwell-Boltzmann. But in a lot of other cases, we have to numerically calculate what this distribution looks like. And if we integrate over this distribution, so here's my distribution of particles in phase space. If we integrate, so we sum them all up, we get the total number of particles. So if we integrate over this full distribution, we get the total number of particles. And then we can take moments of that, which again, we'll go into the moments. But the moment would be, the first moment would just be multiplying the distribution times the velocity. And then the second moment would be taking the velocity squared time this distribution. Okay, so let's keep going. The 6 coordinates, r and v, are considered to be independent variables. We illustrate the definition of f and its phase space in one dimension in figure 2.3 as particles drift in phase space or move under the action of a macroscopic force. They flow into or out of a fixed volume, dx dvx. Hence, the distribution function f should obey a continuity equation, which can be derived as follows. So I'm not going to read every single line in the upcoming because it's a little bit of a mouthful, but before we at least touch on it, the idea is that, again, only showing these two, the particles move out of some sort of phase space region or they move into it. They can flow into it via, they can flow in and out of it either by having a constant velocity and moving out in x, or they can be pushed or pulled out of it by forces. So in this case, electric forces or magnetic forces that push them in and out. Or in a moment, we'll have collisions that instantaneously, not in space, because again, the collision happens over a very, very small space, but the collision will change the velocity. So again, collisions will cause particles to either appear or disappear in and out of it. So um, again, if this is some region of phase space, we can either flow in and out, just by already having momentum, or they can be pushed or pulled by forces, or appear/disappear due to collisions. Now, the collisions are and we'll go real in detail on this in chapter 3, but the collisions themselves are electromagnetic in origin. It's just that they happen over such short time and space scales that we consider them to be instantaneous. So they don't change the position coordinate. They only push in and out of the velocity coordinate. But they are ultimately reducible again to electromagnetic forces. Okay, so again, I will pick up right here. So hence, the distribution function in f should obey a continuity equation, which can be derived as follows. In time dt, particles flow into dx dv across phase 1, particles flow out of dx dv across phase 2, particles flow into dx dv across phase 3, or particles flow out of dx dvx across phase 4. Hence, we can derive this solution here, and then we can simplify it into this solution here, where you basically have a partial derivative with respect to x, or you have a partial derivative with respect to the velocity in x. Now, noting that Vx is independent of x, and assuming that the acceleration ax is equal to fx over m of the particles does not appear on Bx, then 2.3.1 can be rewritten as here. The three-dimensional generalization, so this is for just one dimension. The three-dimensional generalization is given here. Now, this does not have a collision term, so this is without collisions. It's just flow in and out of the phase space, and this is called the collisionless Boltzmann equation, or the Vlasov equation. So in addition to flows into or out of the volume across the faces, particles can suddenly appear in or disappear from the volume due to very short timescale interparticle collisions, which are assumed to occur on a timescale shorter than the evolution of f. Such collisions can practically instantaneously change the velocity but not the position of a particle. Examples of particles suddenly appearing or disappearing are shown in figure 2.3. We count for this effect, which changes f, by adding a collision term to the right-hand side of 2.3.2, thus obtaining the Boltzmann equation. So here we have the Boltzmann equation, and what's cool here is this equation is applicable for fluids as well. So that we can think of the plasma as a fluid. It just has additional body forces that it responds to, namely being the Lorentz force law, so the electric and magnetic field. If this is not a plasma, let's say it's just a gas, then this body force will just be something like gravity that's acting on it. Okay, let's keep going. The collision term in integral form will be derived in Appendix B. The preceding heuristic derivation of the Boltzmann equation can be made rigorous from various points of view, and the interested reader is referred to texts in plasma theory, such as Holt and Haskell. A kinetic theory of discharges accounting for non-Maxwellian particle distributions must be based on solutions of the Boltzmann equation. We give an introduction to this analysis in chapter 18. So uh, again, the solving, so this distribution, I guess this scheme is true of any distribution of f. Now, the Boltzmann distribution, which we'll show in a little while, is only true in certain circumstances. It For more complicated scenarios, you need some sort of numerical scheme to calculate what this distribution should be. So that's why I would say that this distribution, or I said these sets of equations are very kind of fundamental. And then if we can simplify it down further, we can get uh, more tractable solutions. Okay, all right, let's keep going. Okay, macroscopic quantities. The complexity of the dynamical equations is greatly reduced by averaging over the velocity coordinates of the distribution function to obtain equations depending on the spatial coordinates and the time only. The average quantities, such as species density, mean velocity, and energy density, are called macroscopic quantities. And the equations describing them are the macroscopic conservation equations. To obtain these average quantities, we take velocity moments of the distribution function, and the equations are obtained from the moments of the Boltzmann equation. The average quantities that we are concerned with are the particle density. So here, this is the 0th moment. So again, there's 0th because we don't never multiply by the velocity. So here's our 0th moment. The particle flux, which is our first moment, and we can think of this as related to momentum conservation. So we'll develop a momentum conservation equation in a moment. This 0th is particle conservation, and finally, the second moment we can correspond to energy conservation. So the particle flux is given by this equation, and where u of RT is the mean velocity. So it's the mean velocity at some position r. So we can still vary in velocity over space, but at each point, we're going to go ahead and ascribe a single velocity to that point. Same with density. The density can vary over space, but at a single spatial point, we're going to label it with a single density. So, and finally, P of RT is the isotropic pressure, which we define below. In this form, W is the sum of the internal energy density and the flow energy density. So if we imagine some, packet of fluid, it's going to have some energy because the whole packet is moving, but it also has some pressure. If you were to try to, I guess grab it, it would push back to a certain extent, for lack of a better way of saying. So we have some energy that's associated with the pressure, but we also have an energy associated with the fluid moving. Okay, particle conservation. The lowest moment of the Boltzmann equation is obtained by integrating all terms of 2.3.3 over velocity space. The integration yields the macroscopic continuity equation given by 2.3.7. The collision term in 2.3.3, which yields the right-hand side of 2.3.7, is equal to 0 when integrated over velocities, except for collisions that create or destroy particles. So what it's saying, there's different types of collisions. So in an ionization collision, let's say an electron plus an argon generates 2 electrons plus an argon ion. So it'll touch on this in a second, but we have this equation applying to every sort of species. So in this case, there would be a gain of an electron. This should be a positive ion, sorry. There will be a gain of an electron, a gain of an ion, and then there will be a loss of a neutral argon. So we need we need one of these equations for every species. And that's what these gains or losses. For an elastic collision, we assume that there's symmetric elastic collisions happening. So the elastic collision, sums to 0. And that's important for kind of getting a analytical solution to the Boltzmann equation here. So going on, so except for collisions that create or destroy particles, designation as G and L respectively. And he give the ideas, the examples of ionization and recombination. In fact, 2.3.7 is transparent since it physically describes the conservation of particles. If 2.3.7 is integrated over a volume V bounded by a closed surface F, then 2.3.7 states that the net number of particles generated per second within V either flows across the surface S or increases the number of particles within the volume. For common low-pressure discharges in the steady state, G, the gain term, is usually due to ionization by electron-neutral collisions. All right, this is going to be the electron density, and then this will be the collision frequency. So ionization frequency. The volume loss rate L is usually due to recombination, is often negligible. Hence, we kind of get a simplified version here where we only have one gain term. Now, why is this loss low? Well, for low pressures, the um, recombination, so let's say an argon ion plus a negative electron going to an argon neutral, this actually requires a third body mediator to take away the extra energy because energy, if we only have these two collisions, this sort of collision, so this process of argon plus E minus going to argon, energy is not conserved. So you need a third collision to kind of help take away some of that energy. And I'll just call this star for, a third body that has some extra energy. But these three body reactions at low pressure are unlikely. At low pressure, if you think of a gas, an ideal gas has no collisions occurring. So, point being, in a rarefied substance like a gas or a plasma, there aren't that many collisions happening. So there's really only two body. We can consider only two body collisions to be important. Three body collisions are extremely unlikely. This breaks though as you go to higher and higher. Excuse my voice crack. This breaks as you go to higher and higher pressures. You'll start to have three body collisions, and the volumetric loss terms will become important. Okay. However, note that the continuity equation is clearly not sufficient to give the evolution of the density n, since it involves another quantity, the mean particle velocity u. So we can't solve this equation here without knowing u. So we need an additional equation coming from our first moment, and dealing. This sort of relates to our momentum conservation. To obtain an equation for u, a first moment is formed by multiplying the Boltzmann equation by v and integrating over velocity. The details are complicated and involve evaluations of tensor elements. The calculation can be found in most plasma theory texts, for example, Krehl and Trivelpiece. The result is given here. And this is sort of the plasma equivalent of the Navier-Stokes equation. So we have a time rate of change at a position explicitly related to time, and then we also have a change due to just the advection of the fluid itself. We have a term associated with the body force, so this is our Lorentz force. We have a term associated with pressure gradients, and then we have a term associated with collisions. So this is sort of in more of the context of fluid flow. This is kind of where your viscosity term would come from. The pressure gradient would drive macroscopic flows, and then you have a body force. The plasma will respond to electric and magnetic forces. Okay. Left-hand side is the species mass density times the convective derivative of the mean velocity, representing the mass density times the acceleration. The convective derivative has two terms. The first term, du/t, represents an acceleration due to an explicitly time-varying u. The second inertial term from the u, the dot product of u dot grad u, represents an acceleration even for a steady fluid flow, having a spatially varying u. So even if there's not explicitly time rate of change, there will be, if there's a spatial variation in u, there will be a non-zero term here. So, for example, if u increases along x, then the fluid is accelerated along x. Okay, makes sense. The second term is nonlinear in u and can often be neglected in discharge analysis. The mass times acceleration is acted upon on the right-hand side by the body forces, with the first term being the electric and magnetic force densities. The second term is the force density due to the divergence of the pressure tensor, which arises due to the integration over velocities, shown there, where the subscript ij gives the component direction. So this symbol here denotes the velocity average over the bracketed quantity F star. For weakly ionized plasma, it is almost never used in this form, but rather an isotropic version is employed. So basically, there's not, I think from my understanding, and anyone can correct me if I'm wrong, if you get this far in the video and know more than me, these off diagonal terms are basically shears that are driven by the pressure gradients, versus the on diagonal are directly along that dimension. So this would be a pressure gradient in X, a pressure gradient in Y, and a pressure gradient in Z. These off-diagonal terms are shears that can be, placed on the plasma, but we're going to basically ignore that. and simplify it down to, simply a gradient in pressure. Physically, the pressure gradient force density arises as illustrated in figure 2.4, which shows a small volume acted upon by a pressure that is increasing function of x. The net force on this volume, given by this expression, hence the force per unit volume is minus partial derivative of p with respect to partial and x. The third term on the right represents the time rate of momentum transfer per unit volume due to collisions with other species. For electrons or positive ions, the most important transfer is often due to collisions with neutrals. Okay, the transfer is usually approximated by a Crook collision operator shown here, where the summation is over all other species. U beta is the mean velocity of species beta. U mu M beta is a momentum transfer frequency for collisions with specific beta with species beta, and UG and UL are the mean velocities of newly created and lost particles. Generally, UG is much less than U for pair creation by ionization, and UL is approximately U for recombination or charge transfer loss process. We discussed the Crook form of the collision operator further in Chapter 18. The last terms in 2.1.3.14 are generally small and give the momentum transfer due to the creation of destruction of particles. For example, if ions are created at rest, then they exert a drag force on the momentum ion fluid because they act to lower the average fluid velocity. A common form of the average force momentum conservation equation is obtained from 2.3.9, neglecting the magnetic forces and taking U beta equals 0 in the Crook collision term for collisions with one neutral species. The result is given by 2.3.15. So we're basically going to simplify the full kind of Navier-Stokes style equation with only considering the electric fields, only considering the diagonal components of the pressure tensor, and then simplifying to just one collision, drag-related term. So this is our drag, pressure, and body force. Okay. For slow time variation, the acceleration term can be neglected. For high pressures, the inertial term is small compared to the collisional term and can also be dropped. So again, we would like to even simplify this further by ignoring the time rate of change and then also considering situations where there's not large gradients in the flow itself. So we can even simplify this further. Equations 2.3.7 and 2.3.9 together still do not form a closed set, since the pressure tensor P is not, I guess that's pi, and scalar pressure P is not determined. The usual procedure is to close the equations, excuse me. The usual procedure to close the equations is to use a thermodynamic equation of state to relate P to N. The isothermal relation for an equilibrium Maxwellian distribution is P equals NKT, or in just the ideal gas equation, pressure times volume is equal to nRT, so that the gradient in pressure is kT times the gradient in density. This holds for slow time variations where temperatures are allowed to equilibrate. In this case, the fluid can exchange energy with its surroundings, and we also require an energy conservation equation, see below, to determine P and T. For a room temperature neutral gas having density N gas and pressure P yields just a relationship between the density and the pressure in torr. Okay. Alternatively, there's another equation of state called the adiabatic equation of state given here, which relates the gradient of the pressure to the gradient of density here, where gamma is the ratio of specific heat at constant pressure to that at constant volume. These specific heats are defined in section 7.2, with gamma equal to 5/3 for a perfect gas, and for a one-dimensional adiabatic motion, gamma equals 3. The adiabatic relation holds for fast time variations, such as in waves, when the fluid does not exchange energy with the surroundings. Hence, an energy conservation equation is not required. For almost all applications to discharge analysis, we use the isothermal equation of state. Okay. So again, we need some equation of state to help have the same number of equations as unknowns. And finally, to that end, we often need an energy conservation equation, which is our second moment. So the energy conservation equation is obtained by multiplying the Boltzmann equation by 1/2 mv squares and integrating over velocity. The integration and some other manipulations yield equation 2.3.21. Here, 3/2 of pressure is the thermal energy density. 3/2 pressure times velocity is a macroscopic thermal energy flux representing the flow of the thermal energy density at the fluid velocity. Our pressure term here gives the heating or cooling of the fluid due to corresponding expansion in the volume. Q is the heat flow vector. which gives the microscopic thermal energy flux, and the collisional term includes all collisional processes that change the thermal energy density. This is include ionization, excitation, elastic scattering, and frictional or ohmic heating. The equation is usually closed by setting Q equal to 0 or by letting Q be equal just to a gradient of temperature, where kappa T is the thermal conductivity. For most steady state discharges, and this kappa T can be derived using, again, from collisional properties. So that's going to be touched on in chapter 3 as well. For most steady state discharges, the macroscopic thermal energy flux is balanced against all collisional processes, giving the simpler equation here. Equation 2.3.22 together with continuity equations 2.3.8 will often prove self-sufficient for our analysis. All right, great. Yeah, so we need kind of 4 things. We need conservation of particles, conservation of momentum, conservation of energy, and then some sort of equation of state. We may not, depending on the, depending on the how we simplify the problem, we may not need all 4 of those, but that's kind of at most we'll need all 4 of those to solve the plasma. Okay, summarizing. Okay, summarizing results for the macroscopic equation describes the electron and ion fluids we have in their most usually used forms: the continuity equation given by 2.3.8, a force equation given by 2.3.15 with 3 terms: a body force, a pressure gradient, and a collisional term. We have a isothermal equation of state, and then we have the energy conservation equation here. These equations hold for each charged species. Yeah, so remember, we need each of these for each species, with the total charge and current summed in Maxwell's equations. So again, self-consistent. The charged particles contribute to the fields. So when we're solving Maxwell's equations, given at the beginning of the chapter, we need to sum, the densities of each of these and the currents. Okay. So here is our source term for Maxwell's equations. Here's the source current for the Maxwell's equations. Okay. These equations are still very difficult to solve without simplification. They consist of 18 unknown quantities, with the vectors each counting for 3. Various simplifications used to make the solutions to the equations tractable will be employed as the individual problems allow. So one of the main things is we'll simplify down just to single dimensions. And we will do non-complex chemistry. So eventually we want to get to the point where we can handle chemically reactive plasmas, and that generates a lot of different types of species. So you can see how this gets complex. All right, we're almost done. Section 2.4, equilibrium properties. Electrons are generally in near thermal equilibrium at temperature TE in discharges, whereas positive ions are almost never in thermal equilibrium. Neutral gas molecules may or may not be in thermal equilibrium depending on the generation and loss processes. For a single species in thermal equilibrium with itself, in the absence of time variation, spatial gradients, and accelerations, the Boltzmann equation reduces to just the collision operator equal to 0, where the subscript C here represents the collisions of particle species with itself. We showed Appendix B in the solution of 2.4.1 has a Gaussian speed distribution of the form. So remember what I said earlier, if we can simplify the Boltzmann equation, then we can get an analytical solution. And that's what's done in Appendix B. And this is sort of the Boltzmann distribution that we're familiar with, that has this sort of exponential decay. That's a function of the energy up here. The 2 constants, C and chi, or I think it's psi, can be obtained using the thermodynamic relation shown here. I'm not going to read through all of the math here. At some point, maybe we'll go into detail in the Appendix B. But long story short is we can derive an analytic distribution function given here, where we have the energy, again, 1/2 mv squared. We have the energy compared to the temperature. And this is kind of always the case. There's going to be some sort of, the temperature, I always think of it kind of as like a reference scale of the system. And then the velocities will sort of be more or less likely compared to that temperature. Hopefully that kind of makes sense. And we call this the Maxwellian distribution. So it's a single solution to a much simplified Boltzmann equation here. Okay. Similarly, other averages can be performed. The average speed is given here. We get what's called the thermal velocity. Furthermore, we can also get the flux through in some direction here. And we can also get average kinetic energies. Again, this is just sort of the averaging process using that analytic distribution. All right, Boltzmann relation. A very important relation can be obtained for the density of electrons in thermal equilibrium at varying positions in a plasma under the action of spatially varying potential. In the absence of electron drifts, so no bulk fluid motion of the electrons, the inertial, magnetic, and frictional forces are zero, and the electron force balance is from 2.3.15 in steady state given by this equation here. So again, 2.3.15, let's just go back to that really quickly. That's going to be our force equation. And what we're doing here is just getting rid of a bunch of the terms. So it was steady state, so we get rid of this first term. It's no fluid flow, so we get rid of this term here. And then let's see here. I think we got rid of large pressure gradients. So now we just balance the electric field here with collisions. So if we, and I think I just mixed that up. Well, let's see here. No, okay, no collisions. So have no collisions, and we only keep the pressure term and the electric field term, and those have to balance out. And we know because the magnetic field is weak that we can describe the electric field just by the potential. And then we have our equation of state um, given by this solution here. We can plug that in and solve this differential equation for the density of the electrons. And what we get is that the electrons will organize themselves according to the spatially dependent electron potential here, which we call this Boltzmann relation for electrons. We see that electrons are attracted to regions of positive potential. We shall generally write Boltzmann's relation in a more convenient units given here, where the electron temperature is now given in electron volts. The positive ions in thermal equilibrium at temperature Ti, similar analysis shows. So you could do the same thing here, but positive ions are usually not in equilibrium. So hence positive ions in thermal equilibrium are repelled from regions of positive potential. However, positive ions are almost never in thermal equilibrium in low pressure discharges because the ion drift velocity U is large, leading to inertial or frictional forces that are comparable to the electric field or pressure gradients. Remember, inside our plasma, if this is our wall, there's going to be this sheath region that's going to cause the ions to undergo a pretty large, velocity acceleration towards the wall. So this that's what breaks the equilibrium. Debye length. Okay, so Debye length is a very, very important length scale of which if we want to compare one plasma to another, a lot of times we will compare the Debye lengths. So the characteristic length scale in a plasma is the electron Debye length. The other thing I would say too is plasma frequency, which in I think 2 chapters from now we'll derive the plasma frequency. But the plasma frequency is another of these kind of characteristic properties of a plasma. So if I want to compare plasma A to plasma B, I would compare their Debye lengths and plasma frequencies. Plasma frequency being sort of the natural oscillation that the electrons will always have. Yeah. So the characteristic length scale in a plasma is the electron Debye length. As we will show, the Debye length is the distance scale over which significant charge densities can spontaneously exist. For example, low voltage undriven sheaths are typically a few Debye lengths long. So the length of this plasma sheath here will be something like 4 Debye lengths. Yeah. Okay. To determine the Debye length, let us introduce a sheet of negative charge having a surface charge density less than 0 coulombs per meter squared into an infinitely extended plasma having an equilibrium density given by this. So the idea is that we have kind of this region in X where this nice, before we stick in an electrode, the electron density is equal to the ion density. And what we're going to do is we're going to stick in, a boundary that has some negative potential. And then this is sort of like sticking in a Langmuir probe for people that are familiar with that. But if we want to stick in a probe and put it to our own bias, the plasma is going to organize itself around. So the electron it's going to be negative, so it's going to repel the electrons. So the electron density will fall, and then the ions will actually be accelerated into that point. So we're going to basically form a plasma sheath region in this area around the probe that we stick in. And the characteristic length of that is the Debye length, which we'll show now. So for simplicity, we assume immobile ions such that Ni is equal to N naught after the sheet is introduced. However, the negative sheet repels nearby electrons, leading to a reduced electron density near the sheet. The situation after introduction of the sheet is shown in figure 2.5. To determine the potential and density variation, we use Poisson's equation, which in one dimension can be written as follows. So again, Poisson's equation, remember we had grad dot E is equal to rho over epsilon. E is just equal to negative grad times phi. We can do that because the curl, there's basically no magnetic field. So we plug in grad dot E here. That gives us our two derivatives on the potential, and then density rho is just the sum of our electrons and ions. So that's how we're setting up our differential equation. And from the previous section, we derived Boltzmann relation here. So that puts a exponential in place of the basically that allows us to plug in for NE, and Ni is just equal to N naught, and then they pull out the negative sign and rearrange it to get this simplified equation. Now this is a nonlinear equation, nonlinear differential equation. But if let's see here, if phi is much less than TE, then we can do a Taylor approximation. So the Taylor approximation of e to the x is equal to 1 plus x plus blah, 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 x squared, so on and so forth. We just take the first term, 1 plus x. The 1 will get canceled out by the minus 1, and then we're left with simply this equation, simplified differential equation here, which has a nice exponential decay solution. And the characteristic length, the Debye length, is now equal to these properties. So it's increases as the electron temperature increases and decreases as the electron density increases. Okay, so depending on how dense your plasma is and depends on the electron temperature will determine the length scale that this sort of separation between the densities can happen. And we're usually concerned with plasma chambers. So if this is my plasma chamber that has a length L, it'll be much larger than the Debye length, which means that inside most of the plasma here, it'll be quasi-neutral. It's only on the section near the walls where the quasi-neutrality breaks. But inside the middle of the plasma, it'll stay quasi-neutral. Okay, so in practical units, we have it here. With TE in volts and NE in centimeters cubed. All right. The Debye length is useful in many contexts. In the next chapter, we shall see that it serves as a characteristic length scale to shield Coulomb potentials of individually charged particles when they collide. So what that's talking about here is if you have two ions here, their interaction is, by Coulomb's law. And technically they interact at infinity because the Coulomb's law is so strong that it's a 1 over r squared force law. The interaction is so strong that they kind of affect each other at infinity. But inside a plasma, you have the electrons that act to screen out that interaction, and it makes it limits the degree that any two ions can interact with each other. So it changes this idea of the screening, basically changes it from 1 over r squared law to now the product of 1 over r squared times an exponential decay. That's dependent on the Debye length. We'll touch on that next chapter. Although we have calculated the above effect of electron shielding, it is also possible on slower timescales for the ions to contribute. We leave the calculation for a problem. Okay. Ion shielding plays a key role in dusty plasmas, which we will treat in chapter 17. So the dusty plasma, if I, again, have this plasma in here and I have this kind of larger speck of dust, a sheath will form around the speck of dust itself, which is super interesting. And then this also plays an important role for if we stick probes into the plasma. So this is my, if I stick a Langmuir probe, I put it to minus 10 volts, then the plasma will respond in kind and develop a sheath around the probe. Okay, quasi-neutrality. The potential variation across a plasma of length L much larger than the Debye length can be estimated from Poisson's equation given here. We generally expect that the potential is much less than the electron temperature or on the same order, where the equality on the right follows from the definition of Debye length. Combining 2.4.24 and 2.4.25, we have this relation here, going forth, except when used in Poisson's equation. Relation 2.4.7 is the basic statement of quasi-neutrality of a plasma, and it's called a plasma approximation. So basically, if these relationships hold, kind of most importantly, that the length of your plasma, the macroscopic length of your plasma is larger than the Debye length, then we can assume that in the middle of the plasma, it's quasi-neutral. But of course, once we get to the sheath, um, that will not be the case, and phi will actually get much larger than the electron temperature, leading to the breakdown of quasi-neutrality. So again, all this is saying is inside my plasma volume, if the length L is larger than the Debye length, okay, then most of the plasma will exist in quasi-neutrality. It's only at the edge region here that quasi-neutrality breaks, and we have the formation of the plasma sheath. But inside this core region, the electron is approximately the ion density. And to further kind of, it's saying the same thing in a different way, but the potential, if we're going to plot, let's say I take like a trace across the middle here and plot phi versus the potential versus x, inside the plasma, there will be very little potential change. So the delta in the potential, if I take the potential from this point to this point here, will be less. I should draw it as delta. The delta of the difference in potential will be less than the electron temperature inside the main plasma. So it's kind of it's saying the same thing in two different ways. Okay, and then there's problems. So we'll save the problems for the future. But okay, so that wraps that up. Thank you for listening, and I will see you for the next video.